Hello everyone, welcome to my topic Circuits and Networks. I am Ravikant Joshua, and today we are going to deal with an important theorem and its application with the dependent sources called as Thevenin's theorem. In my previous classes, we have discussed basics of Thevenin's theorem. We have seen the definition, we have seen different numericals, how we are going to apply Thevenin's theorem to sort out the problems, and we have compared the result with known as mesh analysis and node analysis, and whatever the answers we got satisfactory with Thevenin's theorem as well as mesh analysis and node analysis. Now with dependent sources, Thevenin's theorem plays an important role. There is a proper procedure to be employed in order to find out the open circuit voltage as well as the Thevenin's resistance. How we are going to do that? We are going to start with the basic numericals, and then we are going to shift to Thevenin's equivalent network. So in my next class, I'm going to deal with Thevenin's equivalent network. In today's class, we'll sort out the problems with basic dependent sources. So this will be treated as class 4, and in class 5, we'll be concluding the Thevenin's theorem. So directly we are going with the problem. We need to find out the current through AB, which is 4 ohms here, using Thevenin's theorem. So this is not as simple or as easier what we have seen with Thevenin's theorem in our previous classes. Here we are going to follow certain procedure in order to obtain the open circuit voltage as well as the Thevenin's resistance. So you can see here we have 2VA. In fact, it is called as voltage controlled voltage source. This VA is represented over which point? This you can see VA is over 6 amperes. It is parallelly connected to 6 amperes. It is also parallel connected to 4 in series with 12 volts. So VA is over here. So this alteration in VA will affect the value of dependent voltage source over this point. So this we need to understand. So our starting problem is voltage controlled voltage source. Since you have voltage VA over here and it is controlling this voltage source, so that is why it is voltage controlled voltage source. Okay. Step 1, remove the load from the given circuit. So we have to remove this 4 ohms from the given circuit. So this is how the circuit looks like. Once this point is open circuited, you can see here you have A, here you have B, and it is open circuited. When it is open circuited, remember, when 6 amperes is driving and 12 volts is driving the circuit, this 2V here will have the impact because of this 6 amperes as well as it is parallelly connected to 4 in series with 12 volts. But this is open circuited. This 2 ohms at that instant of time will have no importance. It will be treated as a dummy only. Okay, because it is open circuited, resistance will be dummy, but the voltage would be present. This voltage would be present. So here we need to find out two parameters: open circuit voltage and Thevenin's resistance. Open circuit voltage is also called as Thevenin's voltage, and Thevenin's resistance we need to find. So these 2 points we need to find across AB. Okay. So let us start the problem with open circuit voltage or Thevenin's voltage. Here we need to find out. Okay. So as I told you, this becomes a dummy resistance. So in fact, you can treat this circuit equivalent to this circuit. Therefore, we need to find out the open circuit voltage at this particular point. And remember, we have VA here. So VA was parallel to 6 amperes as well as it was parallel to 4 ohms in series with 12 volts. So this is what is VA, right? Just have shifted the position, but the measurement will be the same. So VA is over here. The plus and minus indication, it is given in the problem. So if we have taken it is as it is, okay? And we need to find out open circuit voltage over here. This plus and minus sign, this we have assigned ourselves, okay? Now we have to find out VA. So if the current is flowing in this fashion, 6 amperes, it would flow in 4 ohms in series with 12 volts, and that current will circulate in this loop only, and this is open circuited, so current will not flow in open circuit. So if 6 amperes is flowing in this, it will generate a voltage in this fashion. So the voltage will be developed across 4 ohms in this fashion, and already we have 12 volts whose plus symbol is downward direction, minus symbol is in this direction. Now you can apply here a small mesh, or you can apply KVL. Like you have voltage source 12, 4 ohms is having a drop with 6 amperes, so it becomes 4 into 6, and you have measurement over here. So this KVL in this loop we will apply, and we are going to get, see here, 12, this is a 12 volts. Then you have minus it is attained as it is, 4 into 6 plus VA equal to 0. With this, I'm going to obtain the value of VA as 12 volts. Once I'm obtaining the value of VA is equal to 12 volts, I would be it would be easy for me to find out the open circuit voltage across AB. So you will have minus VA plus 2VA plus VOC is equal to 0. Like this you can apply, or you can apply from 12 volts, then drop over here and the dependent voltage source over here, and then you're going to get the value of open circuit voltage. So you can see I have taken the entire loop. 12 volts is a source and minus 4 into 6 is the drop over here. Then we have plus 2VA, that is the voltage dependent voltage source, plus VOC is equal to 0. With this I'm going to get the value of open circuit voltage or Thevenin's voltage as minus 12 volts. Once I'm obtaining the value of open circuit voltage, I have to concentrate on Thevenin's resistance. Thevenin's resistance is obtained in this fashion. Thevenin's resistance is equal to, since the dependent sources problem, so we have a rule that Thevenin's resistance is equal to open circuit voltage by short circuit current. Just now we estimated the maximum voltage, that is open circuit voltage across this terminal. It is obtained across AB as minus 12 volts, and try to find out the minimum current, that is the short circuit current. So this is how we need to find out the resistance for this particular circuit. So this is the major step of Thevenin's theorem with the dependent sources. Thevenin's resistance is obtained as open circuit voltage by short circuit current. So how to find out this? So I'm applying a short circuit wire over here across AB. Now this completes a loop. This 2 ohms, now it gets connected because the circuit is being closed. So naturally we'll be having two loops, loop 1 and loop 2. In those two loops we'll be having current I1 and I2. I1, you can see from inspection, I1 is equal to 6 amperes because direction of the loop current as well as the given source current are one and the same. That is why I1 is equal to 6 amperes. And I2 is nothing but short circuit current. I2 is nothing but the short circuit current. The branch current short circuit as well as the loop current are one and the same. So by inspection, you can get the values of I1 and I2. Now how to solve this? Applying KVL to loop 1. I'm going to apply KVL to loop 1. Since I have I1 over here and VA is given in the problem. So I can apply minus VA plus 4, I1 minus I2 minus 12 equal to 0. Is this clear? So I have applied mesh analysis for loop 1. So with this I'm going to frame my equation in terms of VA and I2. I2 is, remember, it is a short circuit current. So VA plus 4I2 is equal to 12. Now this is equation 1. We have applied KVL to loop 1. Now apply KVL to loop 2. This loop 2. So you're going to get 12 plus 4 I2 minus I1 plus 2 I2 plus 2 VA is equal to 0. So we are taking the value of the voltage, dependent voltage source, as it is given in the problem. So this is the second loop equation, which can be reframed in terms of VA and I2. So 2VA plus 6I2 is equal to 12. Now I have equation 1 and equation 2. I am going to solve these two equations and I'm going to get the value of VA is equal to minus 12 volts and I2 is equal to 6 amperes. Since I2 is equal to I short circuit, naturally the value of short circuit current will be 6 amperes. Now we got the value of voltage and short circuit current. So I'm going to get the value of resistance, which is equal to minus 12 by 6, which is equal to minus 2 ohms. Actually, the magnitude of resistance, if at all you consider, it will be 2 ohms only. This minus symbol we have taken according to the obtained open circuit voltage. Now the things we are going to apply as it is: minus 12 volts, minus 2 ohms. This is the Thevenin's equivalent circuit, and we have connected the load, that is 4 ohms. The load which we have removed from the main circuit, we have connected over here. Thereby the complicated circuit will reduce to simpler circuit, and we get the value of current I is equal to minus 12, that is the voltage, divided by the total resistance of this series network, that is minus 2 plus 4, which is equal to minus 6 amperes. So this is how we solve the problem using Thevenin's theorem, and we got the answer across the load, that is minus 6 amperes. Whether this is right or wrong, that we need to cross check. For that, I'm finding out the current through 4 ohms using node analysis. Okay, already we know that the value of the current here we got as minus 6 amperes. Just we need to cross check the answer which we got using Thevenin's theorem, it is right or wrong, we are cross checking it. So for that I'm applying KCL at node VA. So you can see I'm taking this VA and applying KCL at this particular node. It states that algebraic sum of the currents at a particular node is equal to 0, or the input currents is equal to the output currents, and this is the current we need to find, I. So I will be what? I would be VA minus 2VA whole divided by 6 is the value of current I. So this is what we need to find out. So I'm applying node analysis over here. So node analysis, when we are going to apply this 6 amperes, it is incoming. So that is why it is minus 6 plus VA plus 12 by 4. This is the second branch current over here. And finally, we have I, that is nothing but VA minus 2VA by 6 is equal to 0. By simplification, you will get the value of VA is equal to 36 volts. Once we are going to get the value of VA, then we can get the value of I, as I told you, VA minus 2VA by 6, which is equal to minus VA by 6. When you're going to apply the value of VA, you're going to get the value of current as minus 6 amperes. So you have seen that whether we have obtained node analysis or Thevenin's theorem, we got the value of current which is equal to minus 6 amperes. So this is how we cross check our result. One more method we have, that is mesh analysis. Let us also follow this mesh analysis to obtain the answer, and we'll come to a conclusion that whatever the method we employ, we are supposed to get the same result at the end. So we are going to apply KVL in the loop 1 and loop 2. So when you are going to apply KVL in the loop 1, you are going to get VA plus 4V I2 is equal to 12. This is applying KVL into loop 1. Then applying KVL into loop 2. This is the loop 2. So you're going to get 12 plus 4 I2 minus 6 plus 2 I2 plus 2 VA plus 4, which is making this entire loop parameters is equal to 0. With this, I'm going to get the second equation as 2 VA plus 10 I2 is equal to 12. Solving these two equations, I'm going to get the value of VA as 36 volts and I2 is equal to minus 6 amperes. Remember this I2 is equal to I, which is equal to minus 6 amperes. So now you have seen the result, whether we apply mesh analysis, node analysis, or Thevenin's theorem, or any other theorem, or any other method, we are supposed to get the same current in the particular load. So this is how we cross check our answers. Let us go with another example. Directly we are going to employ Thevenin's theorem. We are not going to apply here again mesh analysis and node analysis like we have done in the previous problem. As a homework, you can solve the same problem using mesh analysis and node analysis. Okay, so we need to find out the current through xy. We need to find out the current, that is 2 ohms. So we are going to apply standard Thevenin's theorem. For that, we are going to remove the load and we are going to find out Thevenins and R Thevenins. Okay, same method. And what kind of source this is? This is a current dependent voltage source. So it can be also called as current controlled voltage source or current driven voltage source, current controlled voltage source, one and the same. Okay, so this is another special case problem. So when it is open circuited XY terminal, as I told you, resistance will behave as dummy in nature. So this resistance will be dummy when the 4 volts is driving the circuit. So we need to find out the open circuit voltage over these particular points. So remember, VOC is nothing but Vthevens. And I'm going to apply mesh analysis over here in order to find out the value of drop over 2 ohms. So if the current is flowing across 2 ohms, so the voltage will be 2 times current I1. So applying KVL, so you can see we have started in anti-clockwise direction. 2 I1 minus 4 plus 2 I1 equal to 0. Since this is open circuited, we don't have any secondary current. So with this, I'm going to get the value of current I1 is equal to 1 ampere. Okay, take it as the resultant 1. And now I'm going to apply open circuit voltage using KVL. So you have minus VOC, this is dummy, so you can remove here, plus 2I1, this is the current dependent voltage source. This current is flowing over here, that is why you have to consider this. So plus 2I1 plus, you can see this is also 2I1 because the same current it is flowing through 2 ohms. So that is how it has changed to 2I1 is equal to 0. With this, I'm going to get the open circuit voltage as 4 volts. Very important and basic way in which you can inspect the problem. Okay, you can comment in the chat box if at all you have finding any difficulty in solving out the open circuit voltage. Okay, now let us find out the short circuit current. Remember, we have R Thevenin is equal to open circuit voltage by short circuit current. So that is why we have to find out short circuit current over this particular load. Okay, So when I have shorted this, I have formed two loops, I1 and I2. Let me apply KVL to these two loops in order to obtain the value of current I1 and I2. Once I1 and I2 are obtained, I short circuit is equal to I2. So we have done this, applying KVL to loop 1. So we are going to get 2I1 minus I2 is equal to 2. Then we are going to apply mesh analysis to this loop. So this is nothing but 2 I2 minus I1 minus 2I1 plus 2 I2 is equal to 0. So which give you the result as I1 is equal to I2. This equation leads to I1 is equal to I2. So when I1 is equal to I2, I'm going to get the value of I1 and I2 is equal to 2 amperes. You can solve equation 3 and equation 4, you will get the same answer as 2 amperes. Once the I2 value is 2 amperes, I can easily say that the short circuit current value is also 2 amperes. So what we have done, we have calculated open circuit voltage, we have calculated short circuit current, and then we are going to find out R Thevenin, which is equal to open circuit voltage by short circuit current. That is nothing but 4 by 2, which is equal to 2 ohms. So this is how we calculate the Thevenin's resistance. Once the Thevenin's resistance is calculated, connect the load which you have removed to the Thevenin's equivalent circuit. Now this is Thevenin's equivalent circuit which has 4 volts in series with 2 ohms. This is called as Thevenin's equivalent circuit, and I have connected the load which is 2 ohms across this, and I'm going to find the value of current which is equal to 1 ampere. So this is how we solve the problems using Thevenin's theorem. Okay, you can apply mesh analysis and node analysis to cross check the result, and you can comment in the chat box if you're getting undesired answer. Okay, and in my next class I'm going to deal with some more examples of dependent sources problems, and we'll finding out the Thevenin's equivalent network for the given network. So in today's class we have dealt with again Thevenin's theorem, especially with the dependent sources. If you like this video, please share among your friends, subscribe to my channel, and please press the bell icon for the future notifications. Thank you.